Welcome to our next lesson. Today's lesson is focusing on functions, as we've talked about. This is the main focus for a while in this course and many chapters. We're talking about what we call recursive and closed form rules. There are two different ways that we can define or describe a function. Now, we've seen many tables in our recent lessons where you've just looked out for patterns and tried to describe them as best you can, which is great because that's what you were doing. You were defining functions. That's what that means. But in mathematics, you know, we like to use symbols often to, I guess, shorten things or maybe not have to use words for them. So let me introduce you to a little bit of what our lesson is going to look like before we dive into an example and some actual vocabulary that we're going to start with. So today's mindset message is to trust yourself. I think in math classes in school, for many of us, our experience is that we're kind of just told what to do or expected just to be able to do something the teacher showed us exactly how to do, but math is much bigger than that. And it's really important that with my guidance, you learn to trust yourself and your ability to reason and to make sense of things and to think deeply. Because honestly, if we're talking from a Christian perspective too, this is exactly what God has designed us to do. And mathematics is such a wonderful subject that we can use to help learn how to do that. Now, when I say trust yourself, I use the word trust because we're going to go through times that are frustrating and challenging, and we have to kind of just push through, but trust ourselves that we can do it, and that we, if we work hard enough, eventually we'll overcome that confusion that we've experienced. So today's learning goals, first we're going to learn to write recursive and closed form rules specifically for linear functions. We're going to learn just what those rules look like, and we're going to use easier functions. And we're going to learn this thing called a difference table that we'll get to later on for a function that's a very useful tool to help us to actually figure out a rule for a function. And then some prior knowledge you want to have is definitely just input-output tables and how we've looked at before and spent some time really thinking about patterns and stuff, as well as using function notation that we've also practiced recently as well. So let's go ahead and dive right in. Here is a table that we've actually seen in the past. And you can look carefully at it. Before you even read these definitions I put up here, here's something that I want you to do. And you can pause the video right now if you just want a moment to think about it, or maybe you've already spent some time looking at this. I just want you to think in your head, whether it's an equation or just in words, is there, or what is a way that you would use to tell somebody what the pattern is in this table? And remember, we're specifically talking about the pattern and the outputs, because we've made the inputs have a pattern just because that's what we like to do. So if we put the inputs in order like this, can we see anything going on with the outputs that will help us to find a rule for it? So you've likely already thought, okay, well, you know, we start with the number 3, and maybe you notice, you know, whether you use this method or not, I saw some of you use this before. Maybe you notice that every time I move to the next output, I'm adding 5 to the previous output, for example. That's a great thing to notice for this one, right? And for most people, I think they see this pretty quickly in this table. Now, that natural method you used where you thought in your head, okay, well, we have to start with somewhere, right? You had to actually specifically indicate that we started with 3, but then you kind of say, well, we added copies of 5 each time. Well, here's the cool thing. Let me ask you, to get to an input of 4, how many copies of 5 did we add on to here? Oh, since this input was technically 0, right? So this is like my 0th output, you could say. Well, then we have 1, 2, 3, 4 copies of 5 that get me to the 4th output. So there's kind of a relationship between the number of 5s and what output we're on. Because we could say the same thing for here. If I want to get to the 3rd output, the 3rd output, this is the input, but the 3rd output, I added 3 5s onto my initial 3. Or to get to the second one, we've added 2. So there's a correlation there that's worth thinking about. So that leads us to our 2 definitions. These are ones you really want to know well, because we will revisit these definitions, actually especially closed form, but recursive multiple times through the year, but closed form we'll use like mostly the whole entire year. So these are really important things to know for the whole course. So recursive rules define a function by giving the starting output. So you basically say, okay, when n is 0, the output is such and such. So we just state that, and we're going to use this. I'll show you some symbols to use, followed by how to get to any output based on the previous output. So it's almost like a staircase. You know, you step up to the first stair. To get to the next stair, I have to step up from the previous one. But how much did I step? So it's almost like this chain link or staircase where you're basically saying, to get to here, I had to, in this case, we had to add 5 from the previous one. And the difference between a recursive, because the recursive is almost like open-ended, right? It's like, okay, all it says is, how did I get here based on the previous one? But it's not as nice in some ways as a closed form rule. Now, they both have their advantages we'll talk about. But a closed form rule instead defines a function directly by giving a formula to use the input to create, to directly calculate its output. So essentially what we want to say is, can I actually use whatever the input is to directly plug that input in to calculate what its output is going to be? And so that's not the way that a recursive operates. So let me actually show you how to write one, then I'll give you an example to practice on your own, and then we'll talk a little bit about some of the advantages and disadvantages of each one of them. So if I were to write a recursive rule for this guy, for this table right here, here's what we're going to do. Now remember, f of n, or, well, in this case n, but we could have used any variable for the input like x is often used, but f of n, a recursive rule actually uses a curly bracket to give the 2 cases. That's an ugly curly bracket. That's better. So remember we said we give the starting output. So we're basically saying we have to start here because unless you give that starting point, you have nowhere to build off of, right? So this is like really like building off of it. So what we say here is we're going to say f of n. Remember, this means output. The output is 3, and we actually use a little bit of words in here, and that's just saying if n equals 0. What that's saying is, here's my starting output. When the input is 0, the output is 3. So in my experience, it's helpful for me to point out to students that this is talking about the output, and this right here is talking about the input, right? And this here, of course, is just the function name, and we're giving it, you know, we're basically describing what the rule is for the function. Now the next thing's going to be a little bit trickier. This is kind of weird because it's almost like a concept that's pretty brand new for people. But bear with me here. So for this one, just answer this question for me. To get to 18, what did I add to the previous output? That make sense? Oh, well, this was 13, and to get here I added 5. And in fact, that's actually true for all of these. This amount we're adding is constant the whole time, right? So no matter what, wherever I'm at, if I'm at 23, how did I get there from the previous one? Oh, I added 5. So this one's all about building it based on an output in relation to its previous output. So this is going to be a little bit weird, but if f of n is specifically representing one output, the previous output is when n is 1 less. So right here, we actually are always going to have, every single time we make a recursive rule, you're always going to have this in the second part. Okay? And what this is, and it's important to remember, this whole thing represents the previous output to f of n. Okay? So this thing right here, that whole f of n minus 1 represents the previous output to f of n. Okay? So for example, if I wanted to calculate f of 4, then if that's our n, then n minus 1 is 3. So what we're saying is, to get f of 4, I need to take f of 3, and in this case, add what? 5. And we could replace 4 with anything. F of 8 would have to be f of 7 plus 5. Okay, so it's just saying, oh, take the previous output and do what to it? So I have to finish this rule off. This purple here, this is the answer for writing a recursive rule. So we say f of n minus 1 plus 5. Remember, 5 is always what is added in our case here. Okay, we'll get to more complicated ones another time. And this we can just say, oh, well, this is true forevermore after that. So we can just say when n is greater than 0. That just means for all inputs after the first input, that's the rule. So I know this is a little bit complex, kind of complicated, but if you look at it really carefully, it's really about reading a new way of writing something, okay? Now let's look at a closed form rule for this same guy right here. This is more like the type of rule you're used to, actually. So I find usually that this comes easier to students. So this closed form rule would essentially be formed by figuring out some formula that directly involves n that I could just plug in any of my inputs to just get its output. So what I'm saying is if I plug in 4, I'm going to get 23. This one is not a direct way, right? So this one, that's one disadvantage. You can't just directly plug things in. It's kind of building on itself. So this one right here, the nice thing is the way we set this up is very helpful. And do you remember how we said there's a direct correlation here between how many 5s we added to get to an output, right? In this case, there's 4 5s to get to the 4th output. There's 3 5s to get to the 3rd output. So essentially, we still think of it kind of like we did the other one. You start with a 3, and you add a certain number of copies of, in this case, of 5. Well, 3 copies of 5 get me to the 3rd output, 4 to the 4th, 2 to the 2nd, etc., etc. So you can probably think, okay, well, if I start with 3, and all I'm doing is adding a bunch of 5s, right? 5 plus 5 plus 5. Well, how many 5s am I adding to get to the nth, right, output? Oh, n of them, right? Because the input is actually matching how many 5s we're adding in this case. So we just say 3 plus 5n. So here's a practice example for you to write a recursive and a closed form rule. Before I let you go on it, here's the table we're looking at. You should notice something slightly different about this table. Besides the numbers being different, and the pattern is a different number that we're adding on, you'll notice that we haven't included any other inputs below 1. So instead of 0 being my first input, 1 is in this case. We'll spend some more time talking a little bit later on how we can make some adjustments to this and stuff. But for now, if we just assume that this is just a sample of some of the inputs and outputs that we could have, that means we could maybe assume that we can go back to 0 and just put in what we think belongs there. So if you look at this pattern, what do you notice we're adding each time in this case? And now, by the way, it could be subtracting, but both of these examples I've given you are adding. 7, right? So to go backwards, I need to be subtracting 7. So what belongs here if my input is 0? 5 minus 7 is -2, right? So now that that's kind of completed, or especially because I have my starting point, I can then build my two kinds of functions. Please pause right now and do it yourself, and then we'll look at the answers together. Okay. Let's check our answers. Remember, a recursive rule always is set up the same way. We always say what's our starting output. So in this case, it's -2. And then we're just going to say if n... Oh, whoops. I made a mistake. If x equals 0, because I'm using x as my input in this case, right? And remember, it's always going to contain in this first thing the previous output. So this represents an output itself, and that means f of x minus 1 represents the previous output. So what am I adding to a previous output to get the next output? In this case, 7. And then this is still the same thing if x is greater than 0. So you'll notice this is looks exactly the same as the last one, Of course, my input variable has been changed, but my starting number is going to be different, and then whatever I'm adding or maybe subtracting to the previous output will change for linear functions anyway. But otherwise, that's it. Let's look at the closed form and check your work on that. Same idea. It kind of starts with my starting number actually, right? It's -2 plus. And remember how we're just adding that same number each time, but how many of them am I adding? Well, it's nice when I can start with 0 or at the 0 input, because then however many of those I add is directly identical to the input itself. So since I'm adding 7, how many 7s am I adding? Well, however many, whatever input I'm at, that's how many. So since that's x, it's simply -2 plus 7x. Okay? Now that's nice because this one, remember this one's kind of just letting me build and build and build. But this one I can directly say, oh, well, what if the input is 100? What if x is 100? I can just put 100 here, and that makes sense. If that means I'm taking -2 and adding 100 copies of 7. And that'll tell me exactly what that output will be at that point, right? Okay, let's think a little deeper. This will be a tad bit more challenging. I really want you to try to take a stab at this yourself, okay? And it's totally okay if you get it incorrect. We're gonna work through it together, but it's really important you've done that pre-thinking on it because that's how your brain gets things to stick, okay? Make a table for this recursively defined function. Now this one's going to look a little weirder. Don't worry about that. And this is weird because it's actually kind of a mix between a recursive and a closed form. Why? Because of this one little piece right here. Now if this was just like this, it would basically look like what we've already had. In fact, we could quickly do it like this just to, check in on that. And you don't have to put this in your notes, but let's see, when n equals 0, it's 8, right? That always gives us our starting output, yeah? And then what this says is, to get another output, I take the previous output. Remember in your head, I'd like you to read it that way. Previous output minus 2. Oh, okay, well, if I want this output, I take the previous output minus 2. You might even be helped out by writing that in there like that. Oh, well, that's going to give me 6, and then minus 2 is 4, and then 2, and then 0. That would be in that case. And then, cool. The nice thing about this is, to be honest with you, even if I have the one that looked a little harder here, like I said, it's almost like this is a mix of a closed form. So this part you could actually plug n in directly and subtract that away from the previous output. That doesn't mean that what that means is what you're subtracting is just not the same thing each time. That's all it means. So instead here, we can still start our table the same, but why don't you go ahead and take a stab on your own and pause right now to try to fill this out based on the original rule I gave you there. Okay, let's check your work. So let's say we want f of 1 right here, yeah? Okay, so this one is literally going to be f of 1. But in order to calculate that, we actually need to take the previous output, which is, what's 1 less, right? 0. F of 0, and we know f of 0, right? That makes sense? Minus 2 times whatever n I'm at, which is 1. In this case, that's going to be 8 minus 2. So that's going to give me 6. Does that kind of make sense to you? And then you can say, okay, well, if I want to get f of 2, it's going to be f of 1, right? Previous output, minus 2 times, now our n has changed to 2. So whatever goes here is f of 2, but what we're going to do is we're going to take our previous output and subtract 2 times 2 in this case. So 6 minus 2 times 2 is going to be 6 minus 4, which is 2, right? And then I think we kind of get the pattern here. So this one, remember, this one was 8 minus 2 times 1. This one was 6 minus 2 times 2. So whatever this is going to be 2 minus 2 times 3, because my n is 3 in this case, right? Well, 2 minus 6 is going to be actually negative 4. So whatever this becomes is that guy, negative 4, minus 2 times n, which is 4. And so negative 4 minus 8 is going to give me negative 12. Okay? So there would be the table for this rule here. 8, 6, 2, negative 4, negative 12. So one last definition and some examples to go with it, and we're done. All right, our definition here is what we call a difference table. Another tool that's going to be super helpful for us at many points through this course. So a difference table is a third column in an input-output table that shows the differences in successive outputs. Take a moment to digest that. If you need to pause and just look through that and think about it, that's fine. But we're going to take a look at exactly what that means. So in our very last example that we're going to do, I'm going to do the first one with you to show you kind of how to set it up, and then I'm going to have you take a stab at the other two on your own. So complete the difference table for each of the following. In order to make a difference table, you take your input and output table, and a third column you make, and the symbol we use here is this like triangle that kind of has that bar on it, and it's called delta. It's a Greek letter that mathematicians have used for a long time to represent the change in something. And that makes sense. And actually, we kind of already did this. Remember when we used the little arrows to represent how much we were going up or down by? This is actually the exact same thing, but just set up a little bit differently. And the way we set it up will actually be helpful for us in the future for things. So this one, simple enough actually, because it's an example from earlier already. So this one, how we fill it out is, from negative 2, what do I have to get 5? Another way to think about it is, it's called a difference table, and you know difference is associated with subtraction, because this minus that gives me this, if that makes sense. Or you could even think this minus this equals that, right? 5 minus negative 2 is 7. I personally find it easiest to kind of ask the reverse question. To get from negative 2 to 5, what did I do? I added 7. And same here, and same here. That guy right there just has what we call constant differences. This stays the same. So now that you kind of see how that works, these ones I've kind of given a little bit different information to really get you thinking about how to make one of these tables. Pause right now and take a stab at these yourself, then we'll do them together, and that'll be it for today. All right, well this one actually also has constant differences, and that difference is negative 6 each time. And so really, since we're given our initial output, it says what to do to get to the next output already. We add negative 6, or you could say subtract 6. So 11 minus 6 is 5. Well, 5 minus 6 is negative 1. And negative 1 minus 6 again is negative 7. You see? So that kind of helps. The difference column actually helps us see some cool patterns that exist in the tables. Now the next one might be a little bit more challenging, but you can really do it. You just gotta, maybe now you looked at this one again and you want to take a stab at C if you weren't sure about it. But let's look at C. I'm going to be off screen a little bit here, but let's think about this. Let's start with this guy here. How can this negative 2 difference help me in knowing this 3? Well, we know that if I took this and I subtracted 2, I got 3, right? This plus that equals that. So what do I subtract 2 from to get 3? That's going to be 5. Now that we have 3, well, I need to know this to even know that. Let's jump down here and see if we can figure something out here instead, right? It's kind of like a puzzle we're working out. So if this was 8 and I added 4 to something to get here, then this must be 4, right? Because 4 plus 4 is 8. And that's nice because then now I have that last missing piece of the puzzle here, because we can just say, okay, 3 plus what gives me 4? That's going to be 1. Okay, so there's everything for this lesson today. Happy math, and we'll see you next lesson.